Alright, so let's start off by reviewing the 4 different types of organic reactions. Those include substitution reactions, elimination reactions, addition reactions, and rearrangement reactions. And then we further went into looking at the different elementary steps that make up these 4 different types. And I want to start by going back over the ones that relate to substitution reactions only. Those elementary steps include bimolecular nucleophilic substitution, or SN2 reactions, and then it also involves coordination reactions. So these 2 elementary steps are only found in substitution reactions. Alright, let's look a little bit closer at the bimolecular nucleophilic substitution reactions, or SN2 reactions. What does this mean? It means substitution by a nucleophile with 2 species. So we have 2 different reacting species in our reaction, which include the nucleophile and an electrophile. And then what are the outcomes of an SN2 reaction? They include a single stereoisomer is formed, inversion of a stereocenter, and so if you have an R stereocenter then you get S, if you have S then you get R. And remember that this occurs via backside attack because our leaving group is partially negative, our nucleophile is negative or partially negative, and therefore like charges repel from each other and you have to get attacked from 180 degrees behind. Alright, so when we approach a synthesis problem and we want to try and decide whether it's undergoing an SN2 reaction, we want to look for a few things. First of all, is our carbon atom that is attached to the leaving group primary or secondary? And so something that looks like this, where our carbon is primary right here, or something that looks like this, where our carbon right here is secondary. If your carbon is tertiary, it will not undergo an SN2 reaction. Secondly, you want to look at the base/nucleophile. If it has a negative charge, then it's probably going to undergo an SN2 reaction, and especially if it's a weak base. An example of a weak base would be something like sodium cyanide. And then lastly, you want to have a polar aprotic solvent that promotes the SN2 reaction. An example of this might be acetone or DMSO. Alright, so let's look at a couple different types of problems that you might see on an exam or something that would proceed via an SN2 reaction. So first thing you want to do when you're approaching a problem like this is look at your carbon molecule and look all around until you find a carbon that's partially positive or partially negative. We see that this carbon here is attached to a chlorine, making it partially positive, and chlorine is also a good leaving group, and so we know that this is the carbon that's going to participate in our reaction. We now need to identify, is this carbon primary, secondary, or tertiary? It is primary because it's only attached to one other carbon group. We then need to look at the things that are over the arrow and see if these would promote an SN2 reaction or not. So we know that primary carbons can undergo SN2 reactions, so that's good. We then look and we see sodium cyanide. We know that sodium doesn't mean anything, so we just mark it out. Put a negative charge on the cyanide. And so we think about this, is it neutral or negative? It's negative, and so that might also promote an SN2 reaction. And then is it a strong or weak base? It is a weak base, therefore also promoting an SN2 reaction. Lastly, we look at the solvent. It's DMSO, which is polar aprotic, again promoting an SN2 reaction. And so we have realized that this type of reaction would undergo an SN2 mechanism. So if we draw the mechanism, we get attack of the cyanide onto the carbon, and we kick off chlorine as the leaving group to give us a compound that looks like this. And so this would be your final product and an answer to a question that looks like this. Notice we had 7 carbons here, and those 7 carbons are still here. And so these are all along for the ride and don't go anywhere. Do not forget those when you're on an exam. Alright, let's move to our second problem down here at the bottom. So if we take the same approach, we look around the entire molecule to try and find a carbon that's partially positive or partially negative. We see that this carbon right here is attached to an iodide, and so we know that the carbon's partially positive and that iodide is a good leaving group, and so this will be the carbon that's participating in our reaction. We want to identify is it primary, secondary, or tertiary. It is secondary, and so we know that secondary carbons can participate in SN2 reactions. So then we want to move over to the things that are above and below the arrow. We look at the top, we see potassium hydroxide. We know that potassium doesn't mean anything, so we just mark that out and put a negative charge on the hydroxide. We think about it, is this neutral or negative? It's negative, and then is it a strong or weak base? It is a strong base. And so these can participate in SN2 reactions, but they might also participate in E2 reactions. And so we need to look down at the solvent. Solvent is DMSO, that is polar aprotic, and therefore promotes SN2 reactions over E2 reactions. And so we've identified that this proceeds via an SN2 mechanism, and so we start with our nucleophile, and we go from electron rich to electron poor, attacking this carbon, and then kicking off our leaving group. Remember that this proceeds via inversion of stereochemistry, and so since the iodide is coming towards you here, the hydroxide nucleophile is now going away from you. And so this would be your final product that you would draw as your answer on an exam. Remember that if this is R, it switches to S, and so if we figure out the stereochemistry here, remember that H is going away from us, so that would be priority 4. Iodide would be priority 1. Our cyclopentane ring over here would be priority 2, and our methyl group would be priority 3. Since priority 4 is already going away from us, we see that this is S. And then remember over here that we have a hydrogen coming towards us, and so if hydrogen is here, it's priority 4, hydroxide is priority 1, methyl group's priority 3, and cyclopentane is priority 2. We see that that looks like S, but since 4 is coming towards us, it is actually R. So remember, in SN2 reaction, we get S to R or R to S, and we get inversion of stereochemistry. Again, don't forget your carbons. Notice that there are 5, 6, 7 carbons here, and there are 5, 6, 7 carbons here, and so we haven't lost any of them. Don't forget to include your carbons when you're on an exam problem. Alright, so the other elementary step that is involved in substitution reactions is coordination. You'll find the elementary step coordination in an SN1 reaction. And so we started talking about SN1 reactions, and I'll go through some sample practice problems here in just a minute. Remember that SN1 reactions do not occur until a carbocation is formed through a heterolysis step. And so this means that only secondary and tertiary carbons can participate in these types of reactions. Because primary carbocations are very unstable and do not form. Remember, the outcomes of an SN1 reaction are that they produce a racemic mixture, and so we get 50% of the R enantiomer and 50% of the S enantiomer. And then rearrangements may also occur. So notice that in SN1 reactions, we have several different elementary steps that can happen. We have coordination, we have heterolysis, and then we have rearrangements. Heterolysis must occur, followed by coordination, or heterolysis must occur, and then rearrangements might happen, and then coordination occurs. And so let's look at some example problems. Alright, so let's do an example problem that you might see on an exam where you would need to go through an SN1 mechanism. And so again, we look at our organic molecule, we look all over the place, and we're looking for a carbon that's partially positive or partially negative. We look around and we see that this carbon is attached to a bromine, meaning that the carbon is partially positive and the bromine is a good leaving group, and so this is where our reaction will occur. We need to identify this carbon primary, secondary, or tertiary. It is tertiary, and so we know that tertiary carbons can participate in SN1 reactions. We then look and see what's over the arrow, and all we have is H2O, and we know that that's neutral, which can also promote SN1 reactions. And so we need to go through our mechanisms. Remember that SN1 reactions start with a heterolysis step. And so for heterolysis, we just kick this bromine off. Boom, off it goes. And then we get an intermediate that looks like this, where we have generated a tertiary carbocation, and our bromine has left. Remember that carbocations are flat, and so when we have our nucleophile come in and attack, we can get attacked from both sides. And so this is the heterolysis step. And that gets us to here. We want to look and see if there's any type of rearrangements that can occur, but we already have a tertiary carbocation, and so it's probably not going to rearrange since there's nothing more stable than that. Alright, so then we have a coordination step, and so we take our nucleophile, which is water in this case, and it goes through a coordination mechanism, and it just attaches to the carbocation. And so this is our coordination step. And then this results in two different products. And so we go from a single enantiomer to a mixture of both enantiomers in the products. And so our two products would look something like this plus this. And so we would have a racemic mixture. When you're on an exam or something, make sure that you draw both of these because we would get a 50-50 mixture of the two. And also realize that the rest of these carbons are just along for the ride, and so don't forget to write those in your product as well. Alright, so let's do another practice problem. So we look at this problem here, and again you want to look around your entire organic molecule and identify the carbon that's partially positive or partially negative. We see that this carbon right here is attached to an oxygen. Oxygen's more electronegative, so therefore this carbon is positive, partially positive. And then we see that this type of group shown down here is a good leaving group, and so our reactions are going to occur at this carbon. We need to identify what type of carbon this is. Is it primary, secondary, or tertiary? It is secondary because it has two different carbon groups attached to it. And then we need to look at what's over the arrow. We see that we have ammonia here, and it is neutral. And so that is going to promote an SN1 reaction. And so remember, in our SN1 reaction, our three elementary steps that are used are heterolysis, possibly rearrangement, and then coordination. And so our first step is heterolysis. Off goes our leaving group. You may also see this leaving group written as OMS, where this is a mesylate, and so this stands for the MS part. Once that pops off, you get a carbocation intermediate that looks like this. So this is heterolysis. Once we get here, we want to think about the possibility of rearrangements. Anytime we have carbocations, we want to think about that possibility. We see that this is secondary, and then we look beside it and see if we can make a more stable carbocation. If we take this hydrogen that is sitting right here, and it rearranges via a 1,2 hydride shift, we would move our carbocation over here. And so a 1,2 hydride shift would give us a molecule that looks like this. Now we've gone from a secondary carbocation to a tertiary carbocation, and this will occur because it is more stable. Now once this tertiary carbocation has formed, our nucleophile can come in and attack. So remember that we go from electron rich to electron poor. Carbocations are flat, so we can attack from both sides. And so we draw our nucleophile attacking our carbocation. And this would give us a final product that looks like this. Notice that we go from NH3 to NH2. That extra hydrogen is picked up by our leaving group so that we have a neutral organic molecule. This is also not a stereocenter because we have two methyl groups here, so there's not four different things attached. And so there's no need to draw dashes or wedges. But remember that SN1 reactions do give a racemic mixture. Alright, so in conclusion, we talked about SN1 and SN2 reactions. And so when you're approaching a problem, the first thing you want to do is see what kind of carbon you have that contains the leaving group. So identify the carbon that has the leaving group, and then figure out if it's primary, secondary, or tertiary. If it's primary and you're trying to decide between SN1 and SN2, primary will always undergo SN2 reactions because a primary carbocation cannot be generated. Tertiary
carbons that contain the leaving group will always undergo SN1 reactions, and because they're too bulky for an SN2 reaction to occur, and tertiary carbocations are most stable. It's when we have secondary carbons that contain the leaving group where we have the most questions that we need to think about. It can be SN2 or SN1. So then you need to look at the charge on the nucleophile or the base, and if it's neutral, it's going to be an SN1 reaction. If it's negative, it's going to be an SN2 reaction. And so if we look at this example down here, we want to look around this entire molecule, find the carbon that's partially positive, and so we look right here, and we see that this carbon is attached to an iodide, and so it is partially positive, and therefore our reaction will be occurring with this carbon. Is it primary, secondary, or tertiary? It's secondary, and so we don't know whether it's going to be SN2 or SN1, but we look at the charge on the nucleophile or base. So we look here, we have H2O and ethanol. Ethanol is our solvent, and so H2O is our nucleophile/base. It is neutral, and so this will proceed via an SN1 reaction to give us a mixture of products. And so we'll get a racemic mixture of these two products. Alright, but what about if we switch up the conditions that we're using? So this time we've taken the same secondary alkyl halide, and so we want to identify the carbon that has the leaving group. That's this carbon right here. And it is secondary because it has two different carbon groups attached to it. So we look up here, secondary can be SN2 or SN1. So we need to ask ourselves, is the charge on the nucleophile/base neutral or negative? So we look down here, we know that sodium means nothing, and so we mark that out, put a negative charge on our cyanide. This means that it's negative, and we're going to undergo an SN2 reaction. So in an SN2 reaction, we have backside attack. We go from electron rich to electron poor, and we kick off our leaving group. Now, since we got backside attack, we're only going to get one product, and it's going to be inversion of stereochemistry. So, over here, our iodide is coming towards us. Now our cyanide is going away. And so this concludes the substitution reactions portion.